Well, hello everyone. I'd like to introduce you to Sam Eng. He's going to be my transmission line today for the intuition for Maxwell's equations. So Sam, let's get this started. Okay, give me a transmission line, two conductors. Here we have two conductors. This is, say, the positive voltage and the ground. Now, what we're going to do is we're going to launch a wave down the line from me, the generator, towards Sam. And here's a picture of the voltage indicated in red, and green is the direction of the current. Sam, which direction is the energy flowing in this setting?
Let me think about it. I think I learned it a few years ago. Is it going to me?
It's going to you. That's absolutely right. So the energy is flowing from me, the generator, to Sam. He'd be sitting at the load. Now, that's all fine. Let's just put this away for a minute. Sam, can you write down the energy that's flowing down the line, the power, the average power?
Well, it's been half a decade since I learned that. Well, let's see if I still have that in my mind. P is 1/2.
Yeah.
The real part
Yeah.
of V times I complex conjugate. Is that correct?
That is absolutely correct.
Wow, no wonder I'm a TA.
That's great. Thanks, Sam. Now, what we want to do is Sam is going to be a transmission line again, but we want to move from voltage and current to fields. So before we set up the line and the directions and stuff, Sam, could you tell the folks out there what V and I will be replaced by when we move to fields?
So I think the voltage sounds to me like an electric field.
Yeah, the voltage is an electric field.
And current, well, current generates a H field, so let's say it's an H field.
An H field. So V is going to be replaced by E, and I is going to be replaced by H. But let's see how that relates to the transmission line. So let's have a look. Okay, so as before, the voltage is between this top plate and the bottom. And that voltage, of course, you have charges here and ground here. So you have an electric field between this plate and the ground plate. And now the magnetic field, well, the current is going in the direction of Sam. So if I use the right-hand rule and curl around, you can see that the thumb is pointing in the direction of Sam along the green. So that means the magnetic field curls around, goes around the top, comes out the bottom. So between the plates, the magnetic field is pointing out. So let's turn a bit so everybody can see that. And so you can now see red is the electric field pointing down. H, the magnetic field pointing in the plane perpendicular to red and green. And green now is where the energy flows in the field. So now, Sam, I need your help. We need to go from V and I to E and H, and I want you to write down what you think P might be and why.
Well, can't we just be straightforward and say P is E times H?
Well, wait a minute. What about the half and the real? Should we put that? Let's put that in.
Let's put that in. A bit crammed.
E times H. Now wait, E and H are vectors, right?
Ah.
So let's put that in.
Then maybe we should do a cross product.
Well, before we do that, let's see what happens if we just keep it like that and put vectors. Put a vector sign over the E and the H. Now, as Sam just said, why do we need a cross product? Well, you can't just multiply two vectors like this because you'll get something very messy. So in this course, we know that multiplication can either be the cross product or what other multiplication can it be?
Isn't there a dot product?
A dot product. The dot product is scalar. And the problem is when we have fields, we want the direction of energy flow, which is from the generator to Sam. So let's put in the cross product. So Sam, thank you very much. This is our first intuitive setting from a transmission line to the fields, and we have an intuitive relationship. By the way, what are the units of E, Sam?
Oh wow, that's really examining me. Let's say it's voltage divided by meter.
Voltage divided by meters. How about H?
Let's say it's current divided by meter.
Yeah, and voltage times amps, volts times amps is what?
Huh, that I think it's power.
Watts
Wattage.
per meter squared. So can you interpret what P is? First of all, P is not a scalar, it's a vector. And it has units
Of watt divided by meter squared. So it's an area.
It's a power per area and it has a direction of flow. So if we want to get the total power, we'll have to do something fancy, like multiply the area by the vector power because it has watts per meter squared.
Wow, this is amazing. I think my knowledge from half a decade ago came back.
Okay.
Hey Matt, what are you doing?
Well, I'm erasing the equation so we can get ready for the next light board.
Oh, okay. Actually, I looked at our video again and I found some errors in what
You
we
mean
did.
we didn't really finish last time? What did we do wrong?
Oh, well, let me go through and show you.
Yeah, I'm curious. Is something obvious that I missed? Let's see.
So last time we started with P equals 1/2 real part of VI complex conjugate,
Right?
right? And then we set that for,
For the fields, right?
yes, for the fields we have 1/2 real part of E, whoops, well that's
E.
not an E, but
Put in an E. Let's take our time here. We're not catching a plane.
cross H, vector,
Vector and vector. We have vector.
Oh.
So what's wrong? Looks okay.
So the issue is we're finding the power,
the phasor power.
the phasor power. So we need to carry on
Oh yeah.
the complex conjugate for
You
the
mean
H.
I forgot, when I was writing, I forgot the complex conjugate on the H.
Well, people make mistakes.
Well, that's really too bad, but this is actually a common mistake. Don't forget the conjugate on the H. And that finishes our intuition discussion. We're going to continue it, though, with a new video showing how this connects equation-wise.
Looking forward to it.
Yeah, right on.